So thank you very much for our introduction. And talking about relationships between humans and technology, I'll start a little bit with that. So I think technology and humans, the relationships, if you think about like Facebook profile kind of status for your relationships, I would say it's complicated. On one side, technology is celebrated. For many years, we see technology as something which gives us hope, right? This technology allows us to fly in the future. It allows us to walk on water in 2000. Now there's also horse walking on water, you should notice. So that gives us better hope, not only for the humans, but also for the horses. And you're going to have the flying cars. You're going to see pictures of Mars. And this is like all amazing. On the other side, and it's going to give you a smoke too, So on the other side, technology is also feared, right? So there's always this fear of technology. People have been trying to save us from technology and explain how we're going to save ourselves for a long time. And it's this fear, we still have this inherent fear of technology. But the reality is, if you look at the history of technology, it's neither feared or celebrated. Usually technology becomes invisible, and then we just stop paying attention. That's what happens to most of the technologies as it goes through cycles of development. If you think about, cities, one of the most amazing technological constructs, right? Power supply, water supply, air monitoring systems. This is an amazingly complex technological system. But if you ask average person, if you ask him, do you think a light in the room is technology? He'll probably say, no, it's not technology. iPhone is technology. Virtual reality is technology, but this is not. And I think computing is following the same path right now. Going from technology to invisibility, starting blending in the physical world around us. And I think work which is done in top research schools and in companies like Stanford and also companies where I work coming from, we're kind of pushing this angle. We went from the computers where you have to wear like tie and suits to even to be close to them, to that's how you used to deliver computers. This is not Amazon. This is something different. To microcomputers where you're not supposed to use, you have a special person to use the computer. To desktop computers, to things you hold in your hands. Now you wear it in your face, and it's going to be part of your body, and it's part of the environment, right? So this progress is inevitable, and this continues accelerating as we're going forward. So the question is, which I've been asking myself for a long time, once computers become invisible, how are you going to interact with them? I mean, there's an inherent conflict between something becoming invisible and you have to use it. Now, this is not a light switch, right? It's not just turning on and off. You actually have to be engaged with the thing, but you cannot see it. So what are you going to do? Are you going to put touch screens everywhere? And that brings another question. The biggest, hardest point about invisible computers is a question of scale. How to turn this technology interaction at scale, not in a single object, but everywhere. If you think about this, displays becoming part of the environment, interaction becoming part of the environment, how you can make it for the whole world, how make it on the scale of a city. We also know how to manufacture electronic gadgets. We knew how to do this for a long time, but we don't know how to manufacture interactive clothes, something which exists in much higher volume, or tables, or carpets, or chairs, or how to manufacture them at scale and still be able to do it going forward. So that's something I've been looking for. One of the few things I've been interested in, and I'm going to talk a little bit about today, is that I've been trying to create interactive technologies and interaction paradigms designed for scale, designed to scale, and that's been my topic for the last 15 years. The way I often pose the research question, in some provocative manner, is that how can we make the entire world interactive? Not an object, but the entire world. What would it take us to make the entire world interactive? But I actually didn't start with that. I started with virtual reality. This is my picture in 1996. That's a real virtual reality display. This is not a Galaxy phone attached to your face. It's a serious thing. It was really heavy too. After 5 minutes, I started sweating. Even at that point, when I was working in virtual reality, it's 20 years ago, I started realizing that the problem with virtual reality and anything when you try to create spatial interfaces is a lack of physical connection, physical feedback to these graphical interfaces. So in this project, we try to bring tablet for drawing inside of the virtual reality, augmented within the virtual reality environment, and try to draw that. That's my student work in early days. I actually published a book about it. I'm very proud of it. But what happens, though, is now with the rebound of virtual reality, and all these new people come into virtual reality, and none of them read my book. So this is kind of something wrong. So I call myself a pioneer, but because nobody read my book, I kind of think the pioneer is a code word for being irrelevant. So, but I'm not bitter about it, because I didn't stay with virtual reality for too long at that time. I moved on, and I was constantly trying to shift myself to the virtual real world, because the problem with virtual reality is scale. Again, it's a problem of scale, because you can only interact with so much content you developed, right? It's much easier to go to augmented reality, and I was part of the AR toolkit. I don't know how much you know about AR. How many of you know about AR toolkit? So I one of the core developers of the AR toolkit team, together with Mark Billinghurst and Dr. Carter in 1998, was done a hit lab. I don't know if you've seen this video. This is the first ever video done with AR toolkit, where we create this card game, and you can pull it off, and the virtual objects appear on top of the card. The video is see-through augmented reality. And that was really engaging. If you actually tried the system at that time on the crappy displays with a very slow update rate, that was amazing. And that's kind of set my trend of my work going toward more of the physical reality, physical world, the physical interaction, rather than staying in virtual reality. So that was at the HEAT lab. And yeah, as I mentioned, it doesn't scale to the real world. So after getting my PhD in playing with virtual reality, I went on and joined Sony. And I was at Tokyo, and I spent 8 years working there. And at that time, in 2001, I was a big proponent of the touchscreens. I thought those touchscreens were going to be the future. Now, remember, that was before iPhone, and nobody believed me. Because at that time, touchscreens were used in a very small number of applications. Cameras, navigation systems, and PDAs, which were coming out from the thing. So to make touchscreen more attractive, we designed tactile feedback for touchscreen. So you can press the button, and you can feel it clicking out of your finger, right? Still, people haven't done this. We've done it in 2001. And at that time, the view of touchscreens was that touchscreen is going to replace buttons. So nobody ever thought about the internet, or browsing maps, anything. The touchscreen is replacement for the buttons, because now you can put buttons everywhere. So this was designed where you can press the buttons on the screen, tactile panel, you can feel it clicking on the finger. And for that, we designed new actuators. It was very thin piezo actuators, multi-layer piezo actuators, because a single layer piezo actuators, you cannot actually make enough force from the voltage which is available from the battery. So you have to go to multiple layers, and there's a lot of complex problems, and electrodes has to be silver palladiums, and they so they don't melt in the baking process of the actuators, and so on and so forth. And what you do with this actuator, you put them between glass and screen, and it bends very rapidly, but a very small amount, and you can feel this force on your finger. You can really feel it's clicking under your finger. It's called Touch Engine. It's published work. I published everything. Everything I do, I usually publish. So you can pull the paper out. And we did actually products. We actually launched this as a component, as Sony was selling it on the market as a unit. And this is a factory which was making. I spent about 2 months in the factory launching this technology, getting it working. It's a cutter which cuts it with a diamond saw, and this is laser navigation system from that. This is our launch party, the factory. This is me. Anyway, and then we did the product. We actually launched it as a product. I'm very proud of it. This is the first ever tactile touchscreen with tactile feedback. Nobody ever before done it, and nobody ever after this done it, right? This is the only one. The only crazy people like myself can do stuff like this. And what happens there is interesting. Is if you look at this design, right, you will see that it has a touch screen with the buttons, tactile, but you can feel them click on the finger, and you have a physical button replicating exactly what's on the touch screen, like this complete copy between these two things. And I went to product manager, I said, like, look, this is crazy. Why don't we have like this? I have this crazy concept. We have this touch screen, and you can have only touch screens, no buttons. You can feel the buttons on the screen. You can scroll through like by moving your fingers on top of that, and it's going to be awesome. Touch screen only interface. And they told me that consumers will never accept a device that has no buttons. So that was the message. And then a year later, ta-da! Damn. And no, but I don't blame them. Now, it's really easy to say like, oh, they don't see the vision, don't understand, blah 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 blah. But the reality is that until Steve Jobs came in with this thing, right? Every single phone, every single device with fully touchscreen was complete failure. The best example is IBM Simon, 1995. Nobody used it, right? No one used it, as a matter of fact. There was only one guy who used it. It was a bad guy from the movie The Net. That's it. The only one user. So the reality is, the reason why touchscreens became popular when they came to use by the masses is because we moved on, and Steve Jobs moved on from the vision of the touchscreen as replacement of the button to give people opportunity to interact with information at scale. Because of the first network-connected devices where you can access the entire internet from your pocket. How can you interact with this information without the size of the table or mouse, right? So touchscreen gave them opportunity. And even though I completely agree, the experience of pressing buttons on a touchscreen is not really good, the opportunity to interact at scale gives power. And that's very important to remember that. And that's why it was successful. But anyway, so I stayed at Sony for a few years after that. We did a few interesting projects. One of them was the concept of bendable computer. We were the first one to come up with the idea that computer can be bendable. So one of the things we did, we put a touch surface on the back of the device, right? So you hold it like this and interact like this on the back of the device. Something that became popular recently. This is a concept for the map, so you can have a map and zoom through the map by bending it. And actually, PS Vita in 2012 used our idea and put a touchscreen on the back of the device. So it's kind of useful. And recently, like bendable phones and bendable displays becoming popular, kind of coming closer and closer to direction. I work on some interactive books. That's the books which record your interaction with the child as you're reading it. I did a shape displays, early work with the shape displays where array of pins would create a physical shape overlapped with light. It was done 12 years ago, 15 years ago, something like that. That was not scalable. So I think the work which is done by Multimedia Lab and Sean Fulmer is much more scalable. They use better actuators. We use shape memory alloys. They tend to break like crazy. And also, you see that some of the buttons, it's kind of bright. Do you think we can turn the light? Because I think it would be possible. So if you see some of the buttons, some of the pins there, you see they're kind of popping up. What happens there, because shape memory alloys, they change the length with current, with the temperature, because inside it gets really, really hot. Some of them start like raising up by themselves. So it was kind of unexpected thing. Anyway, so after that, I went to Walt Disney Imagineering, after Sony, and I was very excited to go because I was getting bored with consumer electronics. It's all about like making millions of things where you have $2 budget. If everything goes more than $2, nobody's interested in talking to you. So I think it'll be kind of cool to work to Walt Disney because number one, it's the happiest place on earth. Right? That's important to remember. Number two, it's giant. Right? It's this massive place, completely artificially created. It's completely fake. This lake is fake. This forest is fake. So we can instrument everything. We have a complete control of the environment. And actually Disney, let's see what I'm supposed to say. Okay. Leslie, Disney was saying, look guys, we're building billions of dollars to build them thing, and then we want to change experience. We want to give people opportunity to change and live through new experiences every time they come to the park. How can we make a physical world as responsive as a computer program, as responsive as the media? So one of my first projects was to think, after spending all these years on touchscreens back in Sony, I thought, well, how can we take touch interaction to the real world? How can we make a physical environment touch sensitive at scale, right? So not at one object, not at two objects, but like everywhere, like the entire Disneyland, touch sensitive all over the place. So this is a project to share. I'm going to show a few videos for you, which I did with Sato, 2012. So to share was this sensor which we invented, where you have a single wire, you connect it to the circuit, and then the object becomes touch sensitive and recognize your gestures. So it knows like you're touching with one finger, with pinching, circle, or grasping, right? Single circuit, single wire, knows what you do with the object, right? You take the same circuit, the same wire, without any modification. You're putting them on the surface of the table, and now it knows how you behave around the table. So scalable because any object can be done interactive. Two elbows, arms flat, sitting straight, user present, using leaves, we all can track it. Again, super simple circuit, very cheap, can do all the stuff. It can also be like surface of the water. So you can take a lot of water in distant land, you can add sensor to the water, and now you can know how a person plays with the water, with 1 finger, with 3 fingers, finger at the bottom, hands submerged, and so on and so forth, right? Can be user body. We can put electrodes on the human body. Now human body becomes also interactive. Again, we don't change circuit, we don't change electronics. Everything becomes interactive just with a single wire. Actually, in case of hand, there are 2 wires. And it can go you can recognize how you're touching your fingers, you're putting them hands together, and even touching your ears, right? So how does it work? It actually made a lot of noise. It was people were quite excited about this work. There was a Arduino version popped up almost like 3 months later. Arduino version popped up, and there's a lot of people using this work for now for the experimentations. So how does it work? It was an observation, which is simple, but somehow was not observed before, is that the path of the circuit, the path of the current, the human body to ground, depend on the impedance. But impedance itself depends on the frequency of the signal. So by changing frequency of the signal, you can send your signal through different parts of the body. And if the body parts changes, you will know that if you compare before and after, right? Very simple idea, never been done before. For the there are reasons for that, but so let me explain how it works, right? So you have one signal that goes this path, this path with the changing frequency, this path, and so on. Then say I cut off your leg. You're a pirate. So what's going to happen is that now the signal is supposed to go through your leg. Now there's a wood, and response will change, right? So by analyzing this response wave, we can know whether you're a pirate or human. So we have a pirate sensor. It can also be used for gestures. So now we did a very simple device where you have electrodes on 2 sides, and you touch them with thumb, touching with thumb with 1 finger, touching with all fingers, and what you get this impedance curves at different frequencies. The impedance measures at different frequencies. They're very different from for each gesture. And now using simple machine learning techniques, you can recognize them and know what exact gesture is doing. Scaling means that every object can be used, right? And one of the things which I was interested to do is to see, can we use something very unusual, like plants? Can you make plants interactive? And of course you can, because plants actually is a naturally grown circuit. It consists of same parts with the same tissue in between. You have a branch. Branch has some sort of nodes, some tissues connecting them, and it's kind of structured as like a circuit. So electrical response at different frequencies will be very unique for each plant, and response to touch is going to be very unique. For example, orchid forms a very natural resistance drop sensor because you have little segments coming after another. Same as bamboo. So it became horticulturists for a while. So this example. So again, the exactly same circuit. You take a little piece of electrode, you stick it to the ground, simply to the ground. Don't have to do anything. Connect it to your circuit here. And now the orchid becomes your sensor. So you can move your hand, you know where you're touching it. So these kind of things you can do. So it has proximity sensing as well. So you can create sort of visual displays which depends how close you're to the plants, how much you engage with the plants. The plants become this interactive medium which grows by itself, non-threatening, and yet responsive and can produce different effects. So I spent a lot of time with this and trying to, you can make a calendar too. I don't know why I would do this. But trust me, it's fun. So anyway, so we tried making different plants. Different plants have different responses. I actually made even a model of the plant. This is a model of the plant from the viewpoint of my sensor. My boss came over. He said, "I like it." So we put on actually in the park. We tried different park scenarios. The different plant has like invited different things. So this is a drum station in Disney Animal Kingdom. So if you're hitting the leaves, it's created this drum sound. It was kind of magical. It wasn't very responsive for different reasons, but it was kind of magical, and kids loved it. So very natural responses. You have to hit with certain strength to get the response, but they very quickly learn it, and they will come back and forth. It's like, oh, look at this, it's a musical plants. So adults are less impressed.
And shut off the sensitivity.
All right. Been there, done that, musical plants, who cares? Good for you. So the proximity is actually important. It senses proximity, and this proximity can also be mapped into the interaction. And we also were trying how it would work during different weather, right? Would it work under the rain? Would it work under how long the plant can live? Do you have to change the sensor? So we left the sensor outside for months, and you can see it works under pouring rain. So there's some sophisticated self-adaptation algorithm which will adapt the plant to change the soil, change the water, and so on and so forth. So I have to force the guy to go out in the rain. So that's the fun thing about working in Disney is that you really focus on experience. You're really focusing on thing being engaging to the user and being sort of inspiring, aspiring. You don't really care about things being useful, but I think this technology can be very useful with plants as well. For example, you can force people to take stairs instead of elevator. Right? If it's a button in the elevator and you have to hurt yourself to call the elevator, maybe you'll take a stairs and save power, but also kind of work out and stuff. That's good. Good for you. So another interesting question, can you go beyond touch? Can you scale tactile feedback? That's the first thing came up after this project. I'm very briefly going to talk about is that, okay, so you can touch everything, but can you create tactile sensations like everywhere? Can you program objects to have tactile sensations? And actually you can. Early work I did at Disney was based on electrovibration. And electrovibration is a force, attraction force. If you have a structure like that, we have an insulator, electrode, and apply high voltage signal to the electrode, you would feel attraction force. And this is, I did the job with you, it's your project. The problem that you have to share the same common ground, or at least you have this ground has to be connected to sort of capacitance or some sort of impedance. But as long as they're close, the strength of this force, as you're sliding your finger on top of an object, is very, very prominent. You can really strongly feel it. Now, what we observed was a very simple observation. Again, for some reason nobody saw it before, is that this equation for the force, attraction force, and if you look at that, the voltage is not directional. The voltage is squared, so it doesn't matter where you apply the voltage. So you can also apply voltage to human and ground an object. So as long as they all share the same ground, which happens in the buildings, as long as they all share the same ground, all you need to do is to attach high voltage signals to the human, so it's always work on you, and ground all the objects, and then you can program environment to have tactile feedback you want. So this is what we did. This is one of the examples of this. So you put in a shoe, we put high voltage circuit in battery in a hill, and this electrode, so you form the same ground connection. And then what you can do, you can, for example, feel textures on random objects in front of you, right? So you can change the texture, and slide your finger on this object, and you can feel this texture on the objects. It doesn't have to be only objects. It can be large surfaces, and any wall can have tactile feedback with the projection, right? So this is impossible to do any other ways. You cannot vibrate the whole wall like we did in case of the remote controller. So this is the only technology which allows to create tactile sensations on arbitrary surfaces anywhere you want. So that was fun. Of course, we can do it on a touch screen, so it's kind of trivial, so I don't want to talk about it. This is an interesting variation of this technology, is that what happens is that if you modulate sound, if you speak in a speaker and modulate sound, and you can rub somebody else's ear, this person will hear sound coming through multiple people. So we made this. For this case, we had absolutely no idea what we're going to do with this. We could not find any possible reason. So we called it art and submitted for Ars Electronica Media Festival, and we got the prize. So it was a happy solution. So, but anyway, so static electricity and electrical field offer some very interesting opportunities. And one of them was question, which is actually quite fundamental question to all of us, is that how can we scale power, right? We can scale interaction, we can scale computations, we can scale all the things, but power is the biggest problem, right? Because we have a power grid. You know, you have safe nuclear stations, for example, providing power, or you can have the solar powers. But in any case, you need wires to run them to your devices. So when you talk about the whole world interactive and everything's going to be interactive and everything's going to be so amazing, well, how are you going to get power to those things? It's a difficult problem. So that was a project which called paper generators, which I did with Kara Gosler, Emery Kara Gosler, who was my postdoc at Disney, 2014. And the idea was there to use humans as a source of power, because humans are plentiful, and then we can use them to make a power. So one idea is to use a kind of matrix style, you know, power concept, but this is kind of a bit too dark from my perspective. And but another approach is actually all approach is to use mechanical motion by human body to produce electrical power. It's like the earliest version of that was a Gibson Girl radio, which was done to pilot during the Second World War, to American pilots, which they would be, you know, when they throw out, being thrown into the ocean, they would use it to create a radio signal. It's actually a very sophisticated device. It had two switches, like which was harder switch creates stronger signal. So while you still kind of in this boat in the middle of the ocean, you still have power, you can create stronger signal. But as you kind of run out of food and water becoming weaker and weaker and weaker, you can switch to weaker signal, but which requires less power. You can still broadcast SOS signal, right? Anyway, so the project paper generators was based on the idea that you can create a very simple electrical generators out of paper. It's a Teflon and Mylar. Very simple things. You just take them together and create certain constructions. So the details in the paper, physics is very complex. So I don't want to go through physics, but they are in the paper. But very simple paper construction out of these materials can create significant power. So this is a button. So you just hit it by hitting the button, you create power. You can power spikes. So what you can do now, you can light up LEDs. Right? So we can create kind of this paper book. So by hitting the button, you can light up LEDs. For example, you can create a game where two people play, and the faster you type, the one is light up, so you win. So very simple interactive games with paper can be created to do this kind of interactions. You can also attach ink display and then turn off and turn off displays inside of the book. Again, no power, no battery, just by rubbing it and creating story, which requires you to rub the page. It requires you to do something. You can kind of create interactive scenarios. By creating a ladder, you can turn them one by one, right? By creating a very simple capacitive ladder. All simple mechanical motion can be done. There you go. And you can do transmission, so you can control your computer from this. So it's a little remote control, so you can control computer from these things. So very simple things. Just practically 5 cents of materials will give you a complete remote control, do all these kind of things. You can also print them at home at printer if you want. And then it becomes, you can light up multiple LEDs if you want. By that time, we actually got very efficient. The LED technology improving so fast because it's driven by electrical lighting. So you can get like really efficient LED these days, which like can do this stuff really easily. So the reason how it works, I'm not going into details. The paper published at WIST about 2 years ago, 3 years ago, we explained the details. But it's very interesting because we all build of the atoms, and there's electrodes. And every time you rub something with your hand, you slide your fingers anywhere, you're ripping electrodes from your body and leaving them on the objects. And it's this thing called, I forgot, electrical proximity. I forgot the name, but some objects, some materials are easier to lose electrodes than the others, and other easier to get than the others. So by using materials with very high difference in these attraction properties, you can actually increase this amount of electrodes coming from one to the other and use them in your circuit. So this is called triboelectric charging, and this is how it was you can always experience when you walk around, you're ripping off electrodes from the table because usually carpet and rubber soles have very high difference, and then you get 3,000 volt minimum charge at the doorknob. So we're using the same technology to create, actually, we insert circuit in between this thing and using the same principle to drive our electrical circuit. It's the effect has been known for a while, but it's amazingly nobody actually exploring this. But there's a lot of interesting stuff you can do with this. We talked about using this for sensors. As you go in there, picking up electrodes from one place and leaving them somewhere else, you can create, where it's like a mark world with electrons you pick up from somewhere else. So kind of this feeling we're surrounded by the ocean of energy, and we just don't know how to pick them up. We're so focused on continuous currents rather than electrostatic and triboelectric charges. And I think it's kind of interesting to see how we can try to save power by using this technology, if it's even possible. Anyway, I want to change a little bit gears here. And I think one interesting thing we'll be looking at back at this is how can we scale displays? Is it possible to create scalable display technology? Because displays are expensive. So is it possible to manufacture some sort of display solution inside of the object by 3D printing? This is a project called Printed Optics, which we did with Carl Willis and Disney. And then here you have we print 3D light pipes into the objects. They 3D print them as objects together to create built-in pipes which can show the images from projector projecting from outside.
Wake up.
So putting displays of this kind of quality.
Like pizza?
He likes pizza. Everybody likes pizza. So putting displays this kind of shape and this kind of size into the objects like that, like a toy, is impossible. So, but creating this light pipe printed in, you can create interactive objects like that. But of course, we did the other things such as controllers and touch buttons and variety of things, all 3D printed kind of optical elements. But we actually went back to eyes, and the reason we went back to eyes is because Disney has a lot of characters around the environment, a lot of characters which stand outside, and all of them have eyes, and eyes is a very expressive interactive element. So how can we bring life to their eyes? And it turns out that if you want to make a realistic eyes, you have to have this kind of Fibonacci-style sequencing for 3D printing, which is actually quite complex. So the mathematics of designing eyes which can be curved, because you need to pack pipes in a tight sequence to create continuous images, was quite difficult. So this is kind of like pipes we were building, 3D printed. And you project from this side, and you can see image on the surface over there. And what happens here is that pipes, they go across up and they kind of spread out to create continuous angles and create very smooth image. So that's how it looks on the toy. So you don't see distortions, and the entire eye kind of is falling up and completely flowing. So this is a character from Tangled, I think. And the beauty about this is because you can take the entire thing and enclose it in the box with a projector, put like a concrete block so nobody steals it, and only have a character on top of it, which can be replaceable, 3D printable anytime you want, right? So this thing is completely passive, and if you look inside, it has nothing, right? All the intelligence is underneath in the box. So this is kind of work we did through for Disney, and sort of after this I went to Google. But this dimension of thinking about how can bring interactivity to the physical world, and scaling interactivity through manufacturing, one through manufacturing, and second through inventing of new sensors, is something I'm very interested in. And I took it to Google when I came to work in ATAP 2 years ago. So in Google, I'm running 2 projects. And I want to finish kind of with 2 projects I'm running now. We announced them at last year, Google I/O. One of them is called Project Soli and Project Jacquard. And I'm going to talk about both of them. So Project Soli. So Project Soli was initially inspired by kind of this desire to scale interaction to very small spaces and wearables, and use gesture interaction, not touchscreens, which touchscreens, again, scaling down touchscreen to very small size is really hard. Like watch is barely unusable, right? How can we create gestures outside of these small spaces? So usually gestures look like this when they connect. So like you have to move your whole body, wave your hand, look like a fool. But the actual gestures we use on small devices look more like this. Sorry. This is how gestures looks when we actually perform something on a very small scale. It's extremely fine. And we usually use tools to interact with these objects, right? We cannot use fingers to build a Swiss watch. And precision and quality of control and the responsiveness of our hand is amazing. We don't have robots are far away, they cannot do anything like this, right? So how can we capture this fidelity of human interaction? And do we have a sensors to even do this? And actually we don't. So to capture the capability of the hand, being able to track very fine motion, to be able to interact in very small spaces, because you don't have much space, but you can project enough information there, was one of the goals to do this. And I'm going to skip that. And what we look at the radars. And the radar is amazing technology because it has very interesting properties. First of all, it can be very precise. You can go to sub-millimeter tracking if you know how to do it, because sub-millimeter tracking. It can track occluded fingers because it tracks motion. Two hands moving like this can be completely tracked, or you can track in front of your hand, in front of your body, and it feels tracked. It can track in 3D. It can track through materials. It's a radar. It goes through plastic, through wood, through everything. You don't care about it's a day and night. And it can be made small enough to fit into the watch, which actually was one of the biggest challenges we had. Actually, let's build it small enough to build in a watch. So that's where radar lives. So our radars we're working on lives somewhere between visible light and somewhere shortwave radio capacity sensing. We're using 60 gigahertz radars. 60 gigahertz radars we're using for multiple reasons. One of the reasons is because FCC allocated widest bandwidth around 60 gigahertz range. 7 gigahertz of continuous bandwidth can be used there, right? And then radar precision depends on the amount of bandwidth you have available. So usually radar is huge. That's how normal radar, this is actually a radio telescope. Doesn't matter, still a radar. So that's how our first prototype we built looked like when we built Soli. Still kind of a box, significant details. So we went through a whole bunch of iterations. It took us about a year to go through multiple iterations of the radars, and we worked with multiple silicon manufacturers. We went through different types of radar, FMCW radars, continuous wave radars, impulse radars, and so on. And at the end, this is our chips, which we introduced at last year, Google I/O. This is a 60 gigahertz 5mm range radar specifically designed for gesture interaction. Right? It's not a radar designed to track a car or a satellite. It's done for gestures. It's the first ever device being done to do something like this. There are two types of the radars because when I started this project, I had no idea if it's going to even work because nobody had done this before. There's no references and there's no kind of previous knowledge if it's possible. So I started with two directions. One was a FMCW radar, and another is DSSR radar. So the important point, which actually was a stumbling block for quite a bit of time, is that we created the radar which packages antennas and circuitry in the same package. So the designer who builds the system doesn't have to figure out how to route 60 gigahertz signal, which is extremely complex and difficult, but everything comes as a single block. So what's output from this radar is so-called bit signal, bit frequency, which is a low frequency signal which you can sample using normal DSP or normal microprocessor. This is how it looks to the manufacturing. We work with Infineon to produce this radar. This is I think it's before packaging, the wafer. And this is our early version of the board with the radar working on the board. You can see, so this is the early version. You can see on the top, we did not have the packaged radar. So you do the die, then you go through packaging process, then you apply antennas. So we did not have the die at the time. So we did a direct die bonding and created and printed antennas separately, which is interesting because it practically means you can create antennas any way you want and define configuration of antennas the way you want, which is the property. So we went from this thing to this thing as actual scale in about 10 months. So we work very fast. Now, what happens is that if you try to redefine the radar for the gesture interaction, you cannot use mathematics which is used for the radar before. It's impossible. Let's see. the typical way to think about the radar is you send a signal to the object and it bounces and comes back to you, right? What happens is that if you want to try, but it works if objects far away. It's a baseball bat, the car, big thing, radar comes. But what happens if you have a hand next to the radar, which is flexible and deformable object, which moves like that around your hand, around the radar? So you have to scan it, right? You cannot just send the signal. You don't get some random reflection, right? You have to scan it like this. And to scan it like this, you have to have a big antenna, or you have to move it, right? And then once you scan it, you get all this data. Processing this signal requires a really high level of computation, which is not available on things like watch or mobile phone or small microprocessor, right? So we had to go and reinvent radar. And I'm not going into the details. This work, we actually just got this work accepted for SIGGRAPH. And I think it's the longest paper SIGGRAPH ever had. It's like 17 pages. So, but that detail is going to be presented there. But basically how it works is that instead of trying to do the pencil beam radar, we illuminate the entire hand with a very broad signal and then see all the reflections coming from different parts of the body forming a shape. As you move your hand, the shape will change. And even though we cannot extract the exact configuration of your fingers to know like which finger moves, the shape itself is going to be unique for the gesture. And by using simple machine learning techniques, we can differentiate the gestures from one to another simply by observing differences in the reflected signal. So that's how that was basic approach to radar sensing, and that hasn't been done before on the level we do it here. So this is our pipeline we showed before. So there's a raw signal from the radar looks like that. So you can see how fast and responsive it is. It's really, really sensitive to motion. And then from there, we compute so-called transformations, which is standard representations. It's like RGB representation for the camera, which is a hardware independent. So one of them, range Doppler, then IQ signals, and spectrogram. And you can see, if you move two hands, you can see two dots moving there because you have multiple reflections coming from two hands. And we do it with a single beam without scanning. And then once you do that, from there we extract features, multiple features we extract from motion on the radar. Let me move a little bit, speed it up. So we extract features from the different part of the radar. So from those images. And again, that's hardware independent, so any radar can be used. And once you extract features, you can put them through machine learning classification with learning and anything post-processing you want to do, filtering, and then recognize the gestures. I'm going to skip that. So that goes to the machine learning algorithms, and then it can recognize simple gestures like this. So this is the entire pipeline. I think developing this pipeline for the radar as a gesture sensor was one of the big contributions of this work, because we just didn't have this before. So what can you do with this whole thing? Actually, you know what? I actually move the slide in the wrong place. So I'm going to show you the slide before. So when we built this radar, what happened is that we had difficulties communicating to people what kind of interactions we can do with this. And slowly we thought like, well, waving hands, how to define these small gestures. And then we had this observation, is that whenever you use your mobile phone, when you use it with one hand, this gesture is so learned and so well known. You know that so well. If you remove your mobile phone, you still can do this quite precisely, right? This is kind of like we're almost ingrained in us culturally, so this kind of gestures. So it's sort of almost like having a mobile phone in your hand, but using your hand as an input device, right? And that's because the metaphor which we came up with is that your hand is a user interface. And what we try to create is replicate motions created by the by physical tools, such as touch panel, or dial, or slider, or button. So, and that became our way to communicate this interaction, where we're talking to the companies and partners and people we're trying to build technology with, is we're saying, look, imagine you have a touch surface in your hand. How does it look like? It looks something like this. And that becomes the way to interact. So your hand becomes a touch panel. Or it can become a virtual control. It can become a dial, right? So if you can track this gesture, then you can imagine the space is filled with different controls and dials, and you can just control them as you want. Or it can be a slider, or it can be a button. So let me show the demos. So this is quick demos which demonstrated about last year at Google I/O. So this shows how the radar reacts. So its presence, you can show how it works. And here we're using this idea of the virtual slider, virtual dial. So when you're rubbing your fingers, just like you do with a dial, you can control this ball on the screen. You can see how precise the motion can be and how fast it is. Very tiny motions of your hand create, can be tracked really distinctly. So now what you can do, you can interpret those motions and create something like this, where you can flick through the image by doing just gesture like that. You can scroll through lists in one direction or in opposite direction. So in this example, what we do, we create two virtual dials, one above the other. So you can control hours with a virtual dial next to the radar, and minutes with the radar, with dial which is higher up. So this way you can start creating multiple controls around your radar using radar as a gesture sensor. Anyway, so I'm going to skip this one. So we released a dev kit recently, and we have a small development community who help us to explore technology. It's still very in early stages. We're still building up the infrastructure and the pipeline and kind of explore the properties of the technology. And I think it's going to go beyond the wearables. It can go into the real world. The beauty about the radar, our sensor can walk up to 15 meters. So, you can imagine everywhere you can put this radar, and sensing can be done and scale at any place you want. But we're starting with a small thing. We're starting with the small wearable devices, and then we think about scaling up to the room scale and maybe city scale and larger scales later as we develop technology developed. So this was the Soli, and this is work we built at Google. And the second project I want to talk about is Project Jacquard. So Project Jacquard takes a slightly different angle on the interaction, a slightly different way to think about it. Is we're trying to manufacture textiles which, by manufacturing, have interactivity built into them. The motivation and and of course, again, making the world interactive is a big idea. And the motivation from there was observation, which I did actually a long time ago. Back when I was at Sony, my boss, Jun Rikimoto, invented a projective capacitive touch sensing, which now used in iPhones. His work is actually widely cited. And it's a grid. The sensor you have in a phone, capacitive touch sensors in the phones, is a grid of electrodes, X and Y direction. And it's know how you touch. Now, we can also observe that textile is also a grid in X and Y direction. So if you replace some of the yarns with conductive yarns, right, what you get is touch panel, which is woven instead of being hard. Right? So you have a complete touch panel solution, which doesn't look like a touch panel, but looks like a piece of textile. And then using this textile, you can build anything you want. For example, you can build a jacket. And because it's done out of this textile, by the company which is making jackets, you would not think about this as a jacket, as a wearable or smart garment. You just think about it as a jacket, right? It's a normal jacket. You don't think about it as something special or interactive, right? Which means that 19 billion garments which are produced in the US market only versus 120 million smartphones, right? Imagine the size of making the world interactive kind of things. If you can reach the goal and make these garments interactive by definition so that fashion industry can use them, 19 billion garments can be interactive, in theory, upper bound. So the big question becomes, can we actually manufacture these interactive textiles at scale? Is it even possible? And in order to manufacture stuff at scale, you have to go through the factories. You have to go to factories, textile factories, and try to make textiles at scale with your interactive garments. So I was traveling around the world. I went to Japan. Went to mills all over the place. This is one of our Japan mills which weaves the stuff. And I will learn the process. And when you weave, I'm going to give you a few details. When you weave textile at the factory versus at home, there is a treatment process very aggressive. In this particular case, they burn textile with open fire to remove excess in fiber, right? And clearly, this is a destructive process not only for textile but also for electronics. So you have to design your yarns and your designs so that it can go through that kind of stuff. And there's many processes like this: there's pressing, washing, stretching, polarizing with certain materials, and so on and so forth, right? Very aggressive. Another problem is the color. So if you talk to any this is kind of a catalog which textile designer gets. This is the colors you have in this catalog. This is kind of colors you get when you buy conductive yarns from the electronics store. So the mismatch, a little bit of mismatch there. So textile designers don't like to use one color. This whole idea is to create multiple textiles. So our yarns, which we designed, can create multiple types of yarns. And we have a very low resistance, it's 0.1 meter ohm per meter, so highest resistance yarns in the world. So the structure we have for yarns is like this. So it's a braided yarns, very thin braided yarns. Again, you can see them here. It's normal yarns, but if you magnify it, it's braided yarns with conductive alloys inside. So that's an interesting story behind the braided yarns, is that we produce them in Japan. And in Japan, they have a long history of making braided yarns. Historically, samurais one of the hobby of samurais in the previous century was bird hunting, right? So you have these birds hunting for prey, and they needed to have very thin yarns to bring them back, but without burdening the bird with extra weight. So these braided yarns are extremely strong, can withstand very aggressive pulling, stretching, and so on and so forth. So Japan has a very low tradition, so that we make them. This is how it looks at my microscope. This is the factory where we're making yarns. You can see how it's made. So designing this kind of process was quite a long time, took us quite a long time. Again, we wanted to do manufacturing at scale, not at a small scale, but actually scale up to the factory. So we went on and we rented half of the floor of a factory in Japan, and that's kind of yarns they do for us now. And the beauty about this is you can make it multiple color, right? So this is all the colors we can produce. Any color you want, any thickness, no, not any thickness, but quite a big range of thicknesses. And we can use them for anything you want. So that's the core of the Jacquard, this scaled manufacturing of yarns, which is designed to be woven into the textile. And this is the first sample of textile we've did at the factory, also in Japan. Actually, Japan is our manufacturing base at this point, for multiple reasons. So the first approach was to try to make textile which completely big grid. And very, very quickly we realized that this is really hard to do anything with this, because how would you connect electronics to this thing? It's like where you're going to pluck the little yarns from the. So we tried this, and this kind of doesn't feel really scalable. So what we went back to the textile core of textile manufacturing, and we suggested we have to manufacture so you can weave panels, interactive panels, where you want them. You should be able to place them anywhere on textile, and it's limited to this area. You don't create the huge panel. You can create a huge one, but you have to be able to control it, and designer can control it. We're using two-dimensional weaving techniques where the yarn runs on the top layer for the conductivity, then it switches layers, it drops on the bottom layer, runs for the brief amount to fix it here, and then floats completely, goes on the third layer, where it's been connected with other type of yarns to keep them together. So what allows us to do, why it's important, is that it allows us to bring us machinery here, which allows us to connectorize the yarn and bring electronics to be able to connect to those yarns. So you don't have to pluck them out by hand, and that can be done automatically at the factory again. So this is a factory which produces our textiles. So design of the process was one of also our know-hows, how to design yarns and textiles so you can weave them at scale. And right now I will show you. Second, we're working with Levi's, and we're working in one of their factories. So the beauty about this process, we can take this and take to any factory in the world, anywhere in the world, and produce interactive textiles. So you don't have to build a new factory. You don't need to buy new machines. You don't need to design new machines. You don't need to modify anything. Any country and any factory in the world can start producing interactive textiles as long as somebody wants it. And we've proven it by actually doing this. So we can make any textile, right? So any type of, this is the type of textile library we made. This is different shapes of conductive areas, and we're kind of raising them up to make them kind of bumpy, so you can have tactile feedback where they are. We can combine conductive yarns with artistic design to create kind of more contemporary designs of conductive yarns. So this area is interactive, you can see, and those are floating yarns over there. We can make wool, different materials. We can make organza, make it transparent. We can make it completely invisible by designing specific structures to do this, or make it stretchable, and we can make it like really, really large. So we can weave tactile surfaces, touch surfaces, as large as you want at different designs. Once you connectorize it through the floating things, you can connect a simple Bluetooth connection, and now your textile can be connected to the mobile phone and become your input to, you can go and control anything in the world, anything you like, from mobile phone to the remote controls to the computers, anything you like, it doesn't matter, robotic arms. So this kind of pipeline, starting from textile structure to connectors to wireless connectivity to mobile ecosystem, people services, that's what we're trying to achieve. A single pipeline which allows to connect textile to people, and textile to services, interactive textile to services. And that's what we're working on right now. That's how it looks like. So as you move your hand, that's what you see on mobile phone happening. Right. So we actually, this is one of the early prototypes of the garment we did. Anyway, so what we also wanted to see is that, okay, so we can make it in the lab. I can bring, the previous garment was done by our in-house fashion designer. I can bring fashion designer and work with her. But what will happen if we give to anybody? Can anyone else, not part of our team, design the garment using this textile? So we went on to Savile Row in London. It's have a history of century-old tradition of making garments, particularly men's suits. And we work with the tailor there to make a garment using our technology. So this is a short video we did. We explain them how that works. We explain what it does. We give them real instructions. Say, okay, go ahead and build something. Design your garment. Design your perfect garment with this technology. So I think designing of the garments, particularly with these guys, these suits cost like $10,000, right? So this is a, not this one, but suits are over there. It's a craft. So people learning it for many years. And then it doesn't change much. They're designing this garment for 200 years, the same way, since the suit was invented. So they were quite excited to see this new technology come into this old craft and allow them to do something new. So they design connections and place inside the garment so you can zip it up. The fit is very important, right? So it has to fit you perfectly. They use my feet because I'm supposed to use it. So make a gesture and make a phone call. So gesture was mapped into the phone call. So of course it doesn't have to be only garments, right? We can scale up to the large environments. This exhibition we did at Google I/O last year, we have woven this giant piece of textile with multiple connection points, interaction points, and they all can control different parts of the environment, displays, and so forth. This was responding to and just showing the shape of the hand as you're touching it. But the point there is that continuously and seamlessly woven without any breaks or without anything, sewing or anything like that. So that's something exciting with making these giant connection services. And we don't think about this technology as electronics. We don't want to position it as electronics. We want to position that as a basic material. So when you go there and there's a label, it says like 85% cotton, 15% Project Jacquard. So you don't think about it as something else. And our first partner to actually take it to the market is Levi's. We announced a collaboration with them last year to bring a garment to the market, first ever mass-produced interactive garment to the market, which allows you to control, well, in theory, anything you want straight from your garment. So this is our VP of innovation at Levi's talking at the Google I/O. And then we are still working on that. Unfortunately, I cannot talk more about what we're planning to do, but trust me, we're working really, really hard to make it happen. Anyway, so this is actually a little bit over time, 5 minutes, so I'm going to have to finish. So this is, I like this quote by Brian Ferren. So technology is stuff that doesn't work yet. Once technology works, it stops being technology. So and I think to become invisible, to actually achieve this goal of invisibility of technology, it has to be flawless, right? It has to be usable everywhere at all times. It has to be inexpensive, consume little power, accurate, easy manufacturing. So it's not one thing, right? It has to hit all those things. And today I was trying to talk about scale, how we can scale up different technologies to use it everywhere. But what's important to understand is that scale is not one-dimensional. It's a multi-dimensional thing. So there's a multiple dimension of scales. And if you want to achieve this invisibility of technology, if you want to achieve this kind of ubiquitous things, you have to optimize technology at multiple scales at the same time. Otherwise, and once you do this, it stops being technology and becomes, something which we will take for granted. And that, I think, is success. Thank you.
Minutes for questions.
Yes.
Hey, so first of all, congratulations on Project Soli and Project Jacquard. It's a really great achievement. My question was towards Project Soli per se. It's a very interesting technology, and you've come up with a lot of new methods of capturing gestures. But I'm really curious to know about how do you foresee this in terms of what gestures are enabled and how that gestures are capable for the market. What I'm trying to say is what do you think? What do you think about what kind of gestures can be used in Project Soli, and how are they more the better fit for the people in the market? You gave an example of the phone, but somebody wants to use it with a computer, or somebody else wants to use it for some completely different reasons. So new technologies enabling new gestures, but what are those gestures?
Right. So as I think I mentioned quickly, so we think about, let me quickly go there. So we have this metaphor of kind of virtual tools. This kind of gestures we're looking at, this kind of our way to classify the gesture. Let me, I'll show it's here. So this kind of the gestures we're looking at, right? This is our kind of roadmap of gestures, where your hand becomes replicates some of the interactions you have with physical tools. So it's a touch panel, dial, slider, and a button. This is pretty much the gestures we're working on right now to build in. And we believe, and this is so how to prove that technology works? The only way to prove that technology works, like on the market, is actually release it on the market, and you'll find out. You're probably going to fall on your face, but it still takes some time to iterate through things. So that's kind of our hope. So that's what we're focusing on. We believe that this is an interesting metaphor because, first of all, it's very difficult to do anything like this with existing sensors on the same kind of level of precision, speed, cost, accuracy, power consumption, easy design, and so on. If you look at all the scales, almost impossible to do anything else. But second thing, it's based on metaphors which we already know from everyday interactions. A child now grows up playing with the touch panels, right? You know how to use dials and buttons from the age of 3, right? It's almost as language now, right? So if it can take this language of using physical control, remove the control, virtualize them, and use your hand as an interaction device, that's kind of our vision to do this. And we're working toward that, but prove and say, okay, I proved that it's going to work. It's impossible until you actually make it a product, release to the market, people are going to use it, and whether they like it or they don't like it, it becomes a question of kind of like, you see. I mean, same story with touch sensors, right? Touch screens. Yes.
Yeah. Cool. So two little things, kind of. Throughout your talk, you mentioned a lot of things where you say, it's funny, no one had ever noticed this before. No one had ever used something before or noticed something before that you noticed. So the first thing, I guess, is what do you kind of think is your key to noticing these things that everyone else glossed over? And then also sort of how because you've probably been doing this your whole life, how have you sort of managed to leverage that best now in your career?
Okay, first question, how I managed to notice this thing. So we all know what serendipity, is correct? No? Serendipity. So serendipity, right? The vision of serendipity is that there's some sort of like, you randomly walk and you hit your head on the wall and you see, oh, there's something there. But that's actually not the actual meaning of the word. The actual meaning of the word is active, the act of looking for something. So I believe that serendipity is an active skill which you can practice, where you're actively looking for the gaps, and things which people don't notice, and try to constantly apply those gaps to what you want to do. So it's one. The second one is, of course, a sort of vision, a sort of direction you want to work on. So I from the very beginning, I always was working on this kind of boundary of physical and virtual. Everything which allows me to create give virtual qualities to physical objects, or give physical qualities to virtual objects. Any of that kind of elements is interesting for me, right? So by using vision and kind of very active, kind of keen observation of the physical reality, where things kind of being overlooked, you can find a lot of things. Actually, there's a lot of things, I've taken notes which kind of like low-hanging fruits, which kind of glossed over, because actually there's a lot of stuff people do, and there's a lot of stuff being just left out. That's one thing. So how I can manage leverage in my career? Well, that's a harder problem. There is I don't know if I have a good answer. I'm an inventor by my spirit and by my training. I'm been doing this all my life. Right now, mostly it gives me opportunity to work in the top research organizations in the world, and to work with smartest people in the world. And in case of Google, I was able to also to build the smartest team in the world. So the people who built Soli, I'm proud to say that we're the top. There's nobody else better than us at this point. And the same with Jacquard. We can do something which nobody else can do. So that's opportunity to create these amazing projects and have leverage based on the credibility I have. That's, I guess, the way I'm trying to leverage this career, in my career. Whether I'm making more money than a hedge fund manager, I'm not sure about it. I don't think so. But that becomes a kind of a question of your values in life. So what is more important for you?
One more question.
It's two questions. It was
Just like a small question. Is the textile washable?
Yes, washable. It took us, I don't want to go into details, but it took us a long time to make it really washable, because textile industry has certain standards for washability. Washability is actually a complex question. It's not just as simple as this is washable. It's not a binary question, right? There's a standards for washability. There's multiple standards. There's multiple standards in different countries. They're different. With detergent, without detergent, cold wash, hot wash, what the temperature. It doesn't include drying. It doesn't include drying. Is it hand wash and hanging outside? Like, this is all stuff. So all stuff is washable. But it takes time to prove it. Yes?
I'm wondering if you can talk a little bit about the cultural context of Soli and Jacquard, kind of in reference to what you were saying earlier about technology being celebrated and feared. Within today's connotations of broadly technology, how do these projects enter that conversation?
I think technology by itself is agnostic to fear and celebration, right? If you ask an average person, do you fear a transistor? The average person would look at you with a blank kind of face, like, what's this transistor? Why I should fear it, right? Do you fear a laser gun made out of transistor? Well, yes, I am, right? It's applications of technologies where we start entering the conversation of kind of cultural domain. Is this technology good for you? Is the technology bad for you? How the radar what's radar going to do when it becomes something? At this point, it hasn't become anything yet. We're working on that. And I think it's up to us to create it in a way so that it's celebrated rather than feared. The very basic question, is it safe? Right? So we spend a lot of time thinking about checking, is it safe? Is radar safe? And it's safe. Both technologies are completely safe. We run through multiple studies and that's it. But I believe the conversation happens, the conversation about cultural aspect of technology start happening when the technology is being applied. And it's too early for that. And I think one of the way to there's two ways to build these conversations. Like there's Apple approach, where you have this crazy control of every single detail to making sure it's completely perfect, and only then you give it to the people. We have a kind of Google approach, where you kind of like let everybody use it, and you release it for open source, and like build the open community, and then you hope that people themselves can regulate themselves to make something beautiful rather than something scary, right? So, I mean, both approaches are valid in some ways.
Okay, let's thank Ivan one more time.
Thank you.